Welcome to this video on the Bohr model. And right here, we've got a little experimental setup of an experiment which was actually being done in Bohr's day in the 1920s, which led Mr. Niels himself to come up with his famous theory of the atom. The Bohr model was created to account for this phenomenon, which I'm about to describe to you right now. So over here, we've got some hydrogen gas in this little container, and we're sending a current through it. That's what this positive and this negative refer to. We're sending a current through this hydrogen gas. And the reason we do that is we want to excite the gas. We want to give it some energy such that it releases light. So over here we've got excited hydrogen gas. Hydrogen gas. And as I said, when gas gets excited, it gives off light. So this hydrogen gas is going to give off some light. And over here we've got just your typical classic prism. You may have played around with these in middle school, and prisms just split light into their components. So if you hold up a prism to the sun, you're going to see a rainbow, because sunlight is made up of the continuous spectrum of all colors which we humans can see. Now you might expect, if we send some light through this prism right here from the hydrogen gas, to see a similar rainbow. But scientists saw something really, really weird. They found that only 5 distinct colors of light were produced by this prism. There was sort of this deep purpley color. There was one that was a little more blue, like that. There was one which was even bluer, like that. There was one which was a little coral color, like that. And there was one which was sort of a deep red color, like that. And so this was absolutely bizarre. And scientists were able to measure the wavelengths of this light. So this is just a little diagram of the light emitted by excited hydrogen. And you can see that it comes at 5 distinct wavelengths. So we've got 1, 2, 3, 4, 5, and these correspond to the 5 colors of light I drew up there. And what we see about these wavelengths is they're certainly not continuous. They're certainly not continuous. There are 5 discrete colors of light which are produced, unlike sort of the infinite spectrum which we see from a rainbow, from light from the sun. This diagram here shows what happens when light is absorbed by hydrogen. So this is light absorbed by hydrogen. So if we shine sort of a flashlight through hydrogen gas, and then say we shined a light through this hydrogen gas, and that light was passed through a prism, this is what we would see. We would get the whole continuous spectrum, so this is the continuous bit, with 5 gaps. And you can see that those gaps correspond exactly with the wavelengths of light produced by excited hydrogen gas. So this is our observation. We see that hydrogen gas can produce 5 specific wavelengths of light when excited, but it can also absorb those wavelengths of light when we send white light through it. And this, ladies and gentlemen, this observation is what led Bohr to develop his model of the atom. And this is what I've got drawn for you here. Bohr's model is sort of the classic orbit model which we tend to think of when we think of atoms. And so this dense center, this red center here, this is of course the nucleus, and Rutherford had already proved that atoms had dense nuclei filled with protons, and then neutrons were later discovered. But the problem of where electrons hung out was still an open question. No one really knew how they were organized. Bohr proposed that electrons could only orbit the nucleus at specific distances, and so he proposed that electrons moved in perfect circles, kind of like we thought planets moved around the sun, and that they could only occupy specific sort of concentric circles around the nucleus. The reason this accounts for these observations we see here is that we can see that electrons can jump between only these specific rings. And as we move up, we see that electrons can gain energy. They're moving farther away from the nucleus, so they're gaining potential energy. So as they move up, they can absorb a specific wavelength of light, because they're always going to absorb the same amount of energy moving from the first ring to the second ring, or the second ring to the third ring. So maybe moving from this first ring to the second ring, an electron will absorb a specific wavelength of light, and that maybe is this red, which we see missing here. And then when the electron moves back down, it jumps back down a level, it's going to give off that light again, and that explains the emission spectrum of hydrogen. And maybe jumping from 1 to 3, that gives off the purple light, and maybe jumping from 3 to 2 gives off the green light, etc., etc. So the big thing you want to remember about Bohr's model of the atom is electrons orbit nucleus. Nucleus. Electrons orbit the nucleus. And Bohr came up with a little equation, which looks like this, to describe the energy of electrons at different levels of orbits. So he said that the energy of an electron was equal to this constant value right here, negative 2.178 times 10 to the negative 18, times quantity z squared, z being the nuclear charge, and n squared, n being the orbit number. Now, because Bohr only created this model for hydrogen, as I wrote here, it turns out that his model didn't really work at all for atoms which weren't hydrogen. The nuclear charge is always going to be 1, because hydrogen only has 1 proton. And this greatly simplifies calculations. But you can see how this works. When we increase the orbital number, or the orbit number, we've got to plug in a different number here, and so the electron is going to have a different amount of energy. And so let's just play around with this equation a little bit, and let's see if we can simplify it. What we're interested in when we look at these wavelengths of light being emitted or being absorbed, we're looking at the change in energy. We're looking at whether the electron gains energy, that is going from 1 to 2, for instance, or losing energy going from 2 to 1, because that's going to produce the emission and absorption spectra, which we looked at earlier. And we know that whenever we have a change in something, that change is just equal to the final state minus the initial state. So we've got energy of the final state minus energy of the initial state. And now we can plug in this expression here for energy into our final minus initial calculation. So we get something like this. Energy final is negative 2.178 times 10 to the negative 18 times 1 squared, 1 being our nuclear charge, divided by n final squared, minus negative 2.178 times 10 to the negative 18 times 1 squared divided by the initial n squared. And now we can simplify this. We see that we've got the same constant in front of both parenthetical terms, so we can factor that out. So we can factor this constant, negative 2.178 times 10 to the negative 18. We can factor that out. And now we can just have a new term. We know 1 squared in both cases is just 1. So now we've got 1 over n final squared minus 1 over n initial squared. Remember, n is the orbit number, the ring, the concentric circle at which the electron is orbiting. And this is the equation we can use to figure out the change in energy when electrons move between orbits in Bohr's model of the atom. Now, we want to use this equation. The real test of this equation is to see if we can come up with these specific wavelengths of light, which hydrogen emits when it's excited. And how do we move between knowing the energy change between electron states and knowing the wavelength of light? Well, because Max Planck gave us this equation, remember this equation describes the energy of individual photons of light, we can actually solve this equation to find the wavelength of light. And we can do that because we know c, the speed of light, is just equal to the frequency times the wavelength. This always confuses me. I always get irritated that this nu here looks like a v, but it stands for frequency. And so if we solve for wavelength here, or actually rather, let's plug this in, solve for frequency. Frequency is equal to c over lambda, and so if we plug this in for nu here, we see that energy is equal to hc over lambda. Now if we solve for lambda, we get wavelength is equal to hc over delta E. So if we know our delta E value, both Planck's constant and the speed of light are constants, we know the delta E value, we can figure out the wavelength of light produced. Let's do a little calculation here to sort of demonstrate how we can use Bohr's equation to figure out one specific wavelength of light emitted from excited hydrogen. So here's the question. Calculate the wavelength of light emitted when an electron drops from n equals 3 to n equals 1 in the Bohr model. So what we're doing here is we're taking an electron at n equals 3, we're dropping it down to n equals 1, and if we're seeing what wavelength of light is produced. We guessed here that it was purple, although I doubt that guess is going to be correct. We will see what wavelength of light we produce. Alrighty, so what's the first thing we want to do? Well, first I'm going to change colors. Now we're going to write our expression for the energy change in the Bohr model. Negative 2.178 times 10 to the negative 18 times 1 over n final squared minus n initial squared. And we can plug in our NF values and our NI values because we know the electron drops from n equals 3 to n equals 1. So we know the final state is going to be 1 and the initial state is going to be 3. So let's plug this in, negative 2.178 times 10 to the negative 18, that's really tedious to write, over 1 minus 3, or rather 1 minus 1 squared, or 1 divided by 1 squared, minus 1 divided by 3 squared. And if we plug this into our calculator, we're going to get negative 1.936 times 10 to the negative 18 joules. So this is how much energy is released when an electron drops from n equals 3 to n equals 1 in the Bohr model. But we want to find the wavelength of light. And to do that, we're just going to do exactly what we did above here, relating Planck's equation to Bohr's equation. And we're going to do something like this. We said that E was equal to hc over lambda. So lambda wavelength is equal to hc over E, and so we figured out this delta E value, and we can now just plug that in to this equation. So Planck's constant is equal to 6.26 times 10 to the negative 34. We're going to leave out units because units are a little complicated with Planck's constant. Speed of light, 3 times 10 to the 8th. And we're dividing by our delta E value. And we're going to take out, actually this is negative because we're dropping from n equals 3 to n equals 1, so the amount of energy, this energy is released. But we're going to make this number positive because it doesn't really make sense to have a negative wavelength associated with a photon of light. That would be crazy physics. So here we're just going to divide by 1.936 times 10 to the negative 18. These are crazy numbers. And we're going to plug this into our calculator and get something like this. Lambda to two significant figures is 1.02 times 10 to the negative 7 meters. And if we want to look at this in terms of nanometers, because a lot of times we deal with wavelengths of light in terms of nanometers, we're just going to multiply this by 100, and we're going to get 102 nanometers. 102 nanometers. So that is the wavelength of light produced when an electron drops from n equals 3 to n equals 1 in the Bohr model. Now, this does not correspond to purple because we know that 100 nanometers is actually smaller than the visible spectrum of something like 350 to 750 nanometers. And so this does not fall in the visible range, but that's okay. It's close enough to visible light to indicate that Bohr's model is correct, because maybe for other drops, maybe from n equals 6 to n equals 4, those are the ones which produce visible light. And so Bohr's equation actually checks out. It can be used to figure out, to predict those precise wavelengths of light which we saw over here. But after going through this entire video and sticking with me, I'm going to break it to you that unfortunately Bohr's model of the atom is just not correct. It sort of works for hydrogen, but beyond hydrogen it doesn't work at all, and we can say by experiment that this is not the way electrons move around the nucleus. But Bohr was pleased with his model, but he ultimately accepted that it was wrong, and so the open question of how electrons moved around the nucleus still stuck around. And if you want to find out the answer to that question, you can check out the orbital video. So thank you very much, and I will see you there.